Okay, we're going to get into some very, very basic ideas of harmonic motion here. Come here, chicken. Meow, meow, meow. Okay, so harmonic motion. Okay, now what makes this complicated is the fact that to do this for real, you need to take at least calculus 2, really cal 3, and differential equations. Differential equations is when you learn to solve these for real. So goal. Take differential equations, except we all call it except that's not a D, we call it diff EQ because we love it. Okay, so just so you know, this is really just a getting fundamentally started with what's going on here. Okay, so first of all, we want to make sure you understand the terms period, frequency. So, you know, you've got a chirp, pretend that's even. Okay, so the time between here and here, like the time between peaks, this is called, I always call it T for some reason. T means period. And the frequency is how often it happens. So, you know, if I take like in 2 pi, there are 3 humps. That means the frequency is 3 humps over 2 pi, something like that. Okay, so the frequency is how often it happens. The period is how long it is between things. And so basically these things are directly related. Like frequency and period are basically the upside down versions of each other. The other word that you might need to know is amplitude. Okay, so amplitude just means how tall something is, and it doesn't matter if it starts out low and goes high. It's just kind of like the absolute value of the height. So these things are always going to be centered. Well, always. Yeah, I'm going to go with always for the purposes of anything you're going to do in the next 3 to 5 years on these. They're always going to be centered on the what do you call it thingy? The x-axis, like maybe not like symmetric, but they're going to be centered, like as much area above as below. So in other words, another way you can hear it is periodic motion, etc. What's another word they're doing here? Phase shift. Phase shift basically means like if it goes over here like a little bit and then you do the exact same thing and it's off by, you know, the same amount every time. Pretend that's the same amount every time. That would be the phase shift. So that's a good start. Yeah, so frequency is just 1 over the period. So if the period, for example, for a sine function, sine of theta, the period is 2 pi, and the frequency is 1 over 2 pi. There's 1 rotation every 2 pi. So, I don't know, that's just straight up, they're exactly the opposite of each other. Period is how long, frequency is how often it happens. The SI unit for frequency is hertz. So, I was describing it more in times of distance, but what we're kind of trying to do here is instead of having it being sine of theta, come here girl, instead of doing sine of x, we're going to really be starting about sine of t. So in the past, or you know what you might be used to is y equals sine of theta, and now we're doing it more like x equals sine of t. So we're really doing position in terms of time, which is how we get to do this whole like physics thing. Okay, so whenever we're talking about frequency, the frequency is how much, the period is how much x distance, but then the frequency is how far between clumps, right? How far between ticks on the board, and so that would be defined in 1 cycle per second. So we're looking at how many cycles is it doing per second, how many, 1, 2, 3, 4, 5, then it's doing 5 hertz, which means 5 cycles, I can't spell, cycles per second. So that's just what hertz means, is a cycle per second. Okay, so we have period, we have frequency. Now in theory, if you took trig in high school, you spent like an entire unit of your life going over stuff like this, and that was in theory to prepare you for getting into stuff like this. Okay, so let's see what happens next. Alright, so the thing is, there's just a bunch of questions I can give you to make sure you understand how to do basically unit conversions of can you convert period to frequency, and these are really straightforward. So what I want you to stop doing is memorizing equations like this, because when you memorize equations, you're not learning anything. What I want you to actually do is think about, well, it makes sense because it either takes this long to do one, or I'm counting how many it does. Let's try this again. I'm either counting how long it takes to do one, or how many I do in a set period of time. So it's kind of like I can work one homework problem every 5 seconds, or in 10 seconds I can get 2 done. It's just kind of like, what are you putting on the top of the equation? So for frequency, you're always going to have the what do you call it, on the bottom. So it's how many per second. So frequency just means per second. How many per second? So the period is 0.4. Now you have to remember that micro is mu, and that's not -3 because that's milli. So let's see, we have milli, micro, centi, milli, micro, nano, pico. -3, -6, -6. So if this is the period, then it's like, so maybe if it helps, we can say the period is, it takes this many seconds per cycle. So and it's going to give it to you in seconds. So it's going to say t is 0.4 times 10 to the -6 seconds per cycle. So the frequency would be 1 over that, seconds per cycle. So then you end up with whatever that ends up being, like 2.5 times 10 to the 6 cycles per second. But you don't have to say cycles per second. You can just do, for shorthand, we say hertz, because cycles is kind of a unitless thing. It just it's like revolutions or stuff like that. Okay, so let's see what we have next. Okay, so the next thing we're actually going to talk about is something called simple harmonic motion. Sorry, I'm in a cafe. Simple harmonic motion, which means that something just does this. Now that's different than damped harmonic motion, which basically means that it fits inside an envelope and slowly does this. This is what happens in real life, right? Because in real life, things don't vibrate forever. They slowly stop vibrating, and they end up actually vibrating in a really cute little pattern that goes like, this is like an e to the -x thing, or a -t thing. Anyway, there's this e envelope, and then things, they rotate, but then they squish inside the e until they stop ringing. We're not doing that because that sounds like a lot of math. And although, this does require calculus is actually not as big of a boy as it likes to think it's doing. So we're really only going to look at simple harmonic motion, which means harmonic motion that stays the same, stays consistent throughout the whole thing. Okay, now whenever you're looking at a mass in a spring, there's usually 2 different ways that you're going to see it. Sometimes you see it where it's hung, and sometimes you see it where it's flat on a table. And so that's what we're looking at right now, is the flat on a table version. Okay, so remember what we talked about with springs, is there's always some kind of like neutral version, like here. And then we talked about, if the spring is, say, over here or over here, then there is a force trying to push it back to its equilibrium position. And I told you to stop paying attention to random negatives and just pay attention to what's physically happening in the problem. So if I'm drawing the free body diagram of the little box here, again, if I'm thinking about this as being like on a flat surface, like not hanging, right here, kx is pushing it toward here, kx is pushing it back. So that would be the force. Now, the other things that, if it's sitting on a, what do you call it, on a floor, kind of like we had. So if it is sitting on the floor, then the other, what do you call it, things on the free body diagram would be, come here, girl, would be your, weight and your normal force, and your weight and your normal force, but it's not moving in the up-down direction, so I don't really care. All right, so if I look at the sum of the forces in the x direction, like the first guy, right now it's accelerating toward the right, it's going this way. Okay, so I can say that the sum of the forces in the x, the sum of the forces are kx, kx, and it's going in the mass times acceleration direction. Come here, girl. Okay, and actually, if I do it for 2, I would end up with, just to show you, I would end up with negative kx, because it's going left, is equal to mass times acceleration, but acceleration is going left, so you actually end up with the same equation, so it's fine. Because really, if you set it off with an initial offset, it doesn't matter if you pull the spring out or you push it in the same amount. If you have a perfect frictionless spring, if I pull it out, a certain distance s, or I squish it in a certain distance s, it's going to look the same. It'll either look like this or it'll look like this. Does that make sense? So it'll either go up first and then down, or it'll go down first and then up, depending on what I'm doing to the spring. Okay, so I do know that kx equals ma, except ma is dv dt, but I also know that v is dx dt, so it's really d squared dt of x, because the second derivative of position is acceleration. So this isn't exactly, what do you call it, too bad, I guess, but I have d squared x dt squared, and I'm just going to say minus k over m x equals 0, and I can't remember if y'all already know how to solve this or not. Maybe not.